through a video. So let's do a recap on what we have covered in the previous lesson on the energy chapter. So firstly, we have identified that there are two different types of energy, namely energy stores and energy transfer. And under each type of energy, there are different forms of energy. For example, under the type energy store, there is kinetic energy, which we have used in many of our example in the previous lesson, GPE. Then, for example, under energy transfer, there are different forms as well. One of it could be the work done, which refer to the amount of energy transfer through mechanical means, right? Then of course there are other forms of energy transfer, such as you have known it quite more familiar to you would be the thermal energy, or what we call heat. So thermal energy and heat refers to the same form of energy. Yeah, so in some lower set, maybe one of your teacher may tell you that heat and thermal energy are different, but actually they are the same. Okay, so then we also learn one law about energy conservation, and that is the total amount of energy actually remain constant, and we actually make use of this to do certain calculation. So for example, in the last lesson, I have introduced to you these two formula for GPE and for KE. Both of these form of energy is energy stores, and I actually tell you that for GPE, you can actually set the H equals to 0 at a convenient spot, so that you don't need to do unnecessary or additional calculation. And then of course there is kinetic energy, right? So I use a example to demonstrate to you how do we use conservation of energy to actually find data that could be difficult to obtain through the Newton's model. That means if you use F net equals to ma, and then you have to use the VT graph to actually obtain this value. So for example, in question 1, we first defined H equals to 0 at A instead of at the ground level. So H equals to 0 need not be at the ground. It can be just at a convenient level, so that you can apply your principle of conservation energy. So for example, here we identified the system as the ball at A versus the ball at B. So because of that, then it becomes quite convenient for us to define the different forms of energy at different state. So what do I mean by at different state? So in energy term, the state refers to the initial state versus the final state. So for example, in this example, A would be our initial state, B will be our final state. So then we move on and we say that, oh, okay, at the initial state, which is the ball at A, it only process kinetic energy in its energy store, right? Because we have defined H equals to 0 at A. So because of that, there's only kinetic energy in the energy store at A. And then when we look at the final state at B, we will be able to see that at B, at the final state, the only form of energy in its energy store would be GPE, right? So based on principle of conservation of energy, we can say that the energy store at A must be equals to the energy store at B. So then after we expand it by our formula, it will become this. Yeah, then of course, some of you, I see that you follow the way I copy 7.2 over here. So like I said, this is not a very good way of writing. It's always good to, align the equal sign in the center rather than to branch out like that. So if you have done that, I would like you to correct it and write it this way. So for me, because I don't have enough space, yeah, so anyway, then after that, we try to frame our question by identifying the initial state and the final state differently. So at C, we now involve the man in the picture, and we say that, oh, whatever energy stored at the final state, which is at B, it must have come from the energy transfer to the ball by the man, right? And we say that this form of energy transfer by mechanical means, like pushing, it is what we call work done by the man, right? So we basically stopped around here, yeah. And I let you try one of the question 2. So now let's begin our lesson today, and let's try question 3. Okay, so for question 3, you can see that the question is trying to say that we are trying to lift up a 12 kg box by a height of 3 meter. So there are two methods. Either you push the box up the slope from the bottom to the top, or we can lift it up by a motor from here to here. So the first thing that most students will encounter is to actually ask yourself, when we are analyzing this, is the box moving? At A, are we talking about, so at A, are we talking about the box already moved or haven't moved, right? So in this case, someone must have pushed it, right? So when you need to push the box, there couldn't be any, the box will not be moving on its own, right? So definitely at the bottom, the box will be at rest, right? Then a person would have pushed it, and how much force is applied, I do not know. But if we are interested to actually, if you look at the question, eventually we are going to compare which box required the least amount of energy. So if you think about this, in order for me to actually use the minimum amount of energy to actually push the box up to here, I have to push the box like shoom, and as it approached the top, I must have slowed down just enough that it reached here. And when it reached the top, immediately I want the velocity to be 0. That would be the minimum amount of force required by me to actually bring this object upright. It's like when you imagine you are a bartender and you want to slide this cup to the customer waiting over here. What you would do is that you want to slide the cup at a speed just fast enough for it to reach the end and stop right at the edge without falling. That would be the minimum amount of energy you require, correct? So because of that, you would want to push the box with just enough force that it will speed up to the top and then speed up to the top and then slow down just enough to reach here, right? So because of that, at the top, velocity is also 0. So how about method B? Method B, if I want to use the minimum amount of motor force to reach B2, well, same thing. When it reaches here, it must be V equals to 0 to get the minimum amount. And of course, since I'm comparing the amount of energy required at B1, the object is also at rest. So actually the first challenge of attempting the energy question is actually how students interpret the question, because most laymen or most beginner will actually imagine that the box is still moving at the top of the slope, or that the box are still moving at the top of the pulley there, right? Or that maybe at the beginning they will think that the object is already moving. So now, by framing it correctly, we can then identify the initial state and the final state. So in this case, obviously, A1 would be my initial state, A2 will be my final state. So down here, I would set my H equals to 0 here. Yeah. So if you look at filling in the boxes in terms of energy store, I would know that my GPE here would be 0, right? Because I'm at H equals to 0. A1, is it moving? So I also know that the energy store, the KE in the energy store is also 0. So you notice that I will fill up this box first, followed by this, right? Because that is the easiest boxes to fill. Then after that, at A2, right? Is that GPE? Definitely, right? Because now I have height, right? As you can see here, I have 3 meter higher than the normal. And but do I have any KE? No, right? Because my velocity is 0. So I know that's kinetic energy is 0. So looking at this, I would be asking myself, at my final state, I actually have more energy than my initial state. So where does this energy come from? It must have come from the energy transfer from the man, right? Because the man is pushing the box up. So I know that this means that there will be energy transfer by the man, right? So I have filled this up, yeah. Then after that, let's look at method B. So maybe now will be a good time for you to press pause, and you can actually try it on your own. So can you pause and try? So I will believe that you have paused and you have tried. So I think very similarly, if you look at case B, method B, at the beginning, you can set h equals to 0 here as well, right? So if h equals 0 and it is already at rest, you would know that the final state here would be no energy, right? Both your GPE and your KE will be equals to 0. And similarly, if you have reached the top, it is already at rest. So because of that, your KE would be 0 because you want the minimum amount of energy. But because you have reached the top, you got more height, at B2 you will have GPE. Then you will also again notice that your final state has more energy than your initial state. So you need to account for where does this additional energy come from, right? This energy must have come from the motor. So now you know that there must be energy transfer by the motor, right, to the box. Let's add in here to be more specific, since in physics, whenever you mention transfer, you should be telling us is from where to where, or by who to where, right? So now if I have this, the question now asks me which method requires less energy to lift the box. So if you look at this, well, the only formula that I can come up with is GPE, right? Is equals to mgh. And since both box has the same mass, m is the same, g is the same, the amount that it get lifted up is actually the same. So what does this mean? This means that whether you are pushing up a slope, or that you are lifting up vertically, the amount of energy is the same, right, by this calculation. But in reality, you would have noticed that if you want to push a heavy object up a certain height, a slope will actually make your life much easier, right, rather than to lift it vertically. So why? So we are going to go into this and answer this question in the next worksheet. So there's a reason. And for the sharper one, do you want to make a guess? So I will let you pause and think for a while as I catch a drink, because my throat hurts. So if you think about it, I think the way we model our energy model is oversimplified, right? There are some things that we didn't account for, and this something that we didn't account for in our model is actually the reason why our calculation does not match how we experience life in reality, right? Number one is when we are pushing up a slope, that the box will be rubbing against the slope, right? So that's friction. Similarly, for your motor, as long as objects are moving relative to one another, there would be frictional forces as well, right? And if you go against the frictional forces, you have to use some energy. Yeah, so we're going to talk more about this in the next part, but let's first simplify our context so that we get used to looking at the context with energy stores and then with principle of energy conservation. Okay, so let's fill this up, right? Determine which model requires less energy. You will notice that the amount of energy required, right, depends on the gain in GPE, which is the same for both cases. So in another word, both methods require the same amount of energy. Yeah. So why I want to put this question here is that I just want to show you guys sometimes when you are doing physics question with a context that seem like reality, and then you try to apply how you experience life and you try to answer the question, you will find that you get wrong answer. And the reason is because with the content that we have taught you, uh when we present a context to you, actually we actually really need to do a lot of simplification to an extent whereby if you look at uh the working, you will come to a conclusion that doesn't match how you experience life. So because of that, try to avoid applying common sense when you are solving a physics question in a exam or a homework setting, because most likely uh, you will have contradicting conclusion. Yeah. So let's move on. We have some checkout activity. What I want you to do is I want you to pause the video and I want you to try this question. What I can do now is that I can give you some hints, and then there will be a part 2 video where I go through this question. So if you need hints, here I can give you some hint. Down here, you can set h equals to 0 here, and your calculation will be much easier. And for here, be mindful that the object is already moving. So down here, if you take this as the initial state, you should have two form of energy. Okay, and down here, you can set h equals to 0 here. Excuse me. For question 3, really, I want you to think deeply before you make any assumption. Remember what I just said. When it comes to academic context and real life context, there may be some different. So when you do question 3, I just want you to recall your experience to this question. Okay, so take a pause and go and try out the checkout activity. After you do it, you can watch the part 2 video. Okay.